for the introduction, and I might have to change that because there's no such thing as my current research right now. This is what I spend most of my time on. Well, good morning, everyone. So I will be. This is going to be kind of an overview of what CESM is and a little bit about how we build it, just in general, but also some of the more recent development in building CESM, the second version of the Community Earth System Model. Don't have a pointer, but it's okay. I've got long arms. And before I start, I really have to say, so the front slide only has my name, because if I start putting names, it's going to take pages and pages, and I will forget someone. So instead, I'll just have a blanket statement. But this is really, as a chief scientist, I'm mostly there to try to get things moving, and then when decisions have to be made, and then I'm the one making the decisions. But usually, we try to work in a very collegial fashion. And CESM, so there's a bunch of Earth system models out there, right? So if you look at the work that goes into IPCC, there is like 25 plus modeling groups around the world, and they're all building different varieties of Earth system model. One thing I find that CESM is different is that it really, on top of being built by the community, but also it's not just built by the community, but it is being used by the community, and the community is really at large. And we're trying to not just have like top of the line, state of the art science and the highest resolution we can get, but we're actually trying to have a tool that can be used by a variety of people over a variety of platforms. And so that goes from something that you can run on your desktop or laptop, which is something like a single column version, so just reducing the whole world to just one vertical column. And that gives you, that's a good test bed if you're looking at atmosphere parameterization. Right? You want to look at clouds, and this might be, you might be able to compare with observations at a single site. So this is kind of a like physics development test bed. And also some really coarse resolution. I mean, we don't advocate people to use those really coarse resolution versions because they might not be representing dynamics of the atmosphere or the ocean well, but sometimes it might be well enough for the question of interest. And so there's still some versions out there, like 10 by 15 in the atmosphere, so 1,000 kilometers grid size. But then it will run on your laptop. And so there is still something that can be learned, if nothing else, as a teaching tool. So there is a lot of this that can be used in classes. And then a more slightly like lower resolution than what we would be using in this variety. And so for large ensemble, paleoclimate, although more and more we're moving into the standard resolution, and just what university has access to might be just a small cluster. They might have their own cluster, so they cannot maybe do as much as we want on high resolution. So what we're trying to do is to build something like this, right? So that on top of building this, we need to make sure that all this works so that all the people interested in working in the development of CESM can participate. And this is just that my one slide on the CESM governance, because so you want to get input from the community. What is the way to make that happen? Well, we have 12 working groups. The white ones are all the ones that are more related to the development of specific parts of the model, like the atmosphere model. And then the other ones are more what we would call applications. So paleoclimate, climate variability, so those are people doing the analysis. And that's one thing that's critical in building a model, is that it's not just writing code and putting code in place, it's having the support from the people who are going to be running it. They're going to be testing it, they're going to be analyzing it. And so feedback on what works and what doesn't. It's not always easy for each of those groups to get the full picture of what is going on. So some numbers, we tend to run, most of the model that I will be talking about is 1 degree, 100 kilometers in the horizontal, and we have exploration at higher resolution, 1/4 degree, that's for the atmosphere. And we also, again, providing this to the community, a 2 degree version. But this is what I ended up calling our workhorse. And at those resolution, it's about a 30-minute time step. So all the laws of physics that we can think of and chemistry, whenever it's needed, are solved every 30 minutes. We go from the surface to about 40 kilometers in our standard version with 32 levels. And then there is the whole atmosphere version, which goes up to 150 kilometers, and that has 70 levels. The ocean tends to be run at 1 degree, same as the atmosphere, or 1/10 of a degree. And those are the standard configurations for the present ocean model. So that's like, in terms of code itself, it's 1.5 million lines of code. And yes, it's Fortran. I don't think there are any lines of C or anything else in there. It might be old Fortran. It's not all Fortran 90 or newer. And then the data ends up being generated usually on monthly timescales because a lot of the simulations that we do are long-term simulations. So we do a lot of monthly, but then to really understand the processes, you want to have high frequency daily or even hourly. And then this generates terabytes of data. But it is used by hundreds of scientists around the world. And I think as such, it's a really nice success. And so this is an evolution, obviously. We're CESM2, before clearly there was CESM1. And then there was the Community Climate System Model, CCSM, and the CSM. And so a lot of that relates to what are the main processes that are being represented in the model. And so the break between the climate and the Earth system model started when we started putting things that, in a way, required more than just the Navier-Stokes equations and thermodynamic, and you started looking at aerosols and biogeochemical cycles. In a sense, you needed to represent a lot more than just winds and temperature and humidity. And so the model development is like a balance between bringing more and more processes. I mean, the idea is to have basically a lab that you can use to test hypotheses, right? So this is why we build a model. We want to test hypotheses, and we want to make sure that whatever we build has the features that we feel are representative of how the real world functions. And so we've been adding processes because we feel those processes are important to capture the feedbacks and the interactions between the different parts of the model. So there is this evolution towards more and more complexity, and at the same time, we know that increasing the resolution enables the model to represent explicitly more and more features. And so there is always the tendency of increasing the resolution with the hope, and it's not always fulfilled, at least not initially, with the hope that it improves the quality of the model. Right? Some aspects will improve, some aspects will degrade, mostly because of all those representations of subgrid. So all those parameters like clouds are much smaller than the size of the grid, right? So, and then you can tune it, you can really develop it for a certain resolution, and then change resolution, and it doesn't work as well. So then there is additional work that has to be done. And we're a long way from being able to represent it to the level where we would not need any of that. So larger dissimulations that people are doing are in the meters range. So not fast enough to compute the number of grid points that would mean on to represent the Earth on a largely simulation resolution, but it's just untractable at this point. Maybe in 20, 30 years, but nothing right now. And then one thing that I think has been kind of really annoying for us in a way is this ensemble thing. And the ensemble is, I'm just going to discuss what we're talking about here. So the ensemble is really trying to capture some knowledge of the internal variability of the system. And so this is one example of looking at what that variability means. So say you run the model in pre-industrial with 1850 conditions, and it's perfectly stable, right? Has those little wiggles. This is the global surface temperature. Has those little wiggles. Weather traveling around the world. Some rearrangement between the ocean and the atmosphere. And then you start having the 20th century simulations going into the 21st century. And in this experiment here in 1920, you stop the model, and then you put a 10 to the minus 14 perturbation to the temperature field everywhere. So that's like one of those small digits. And then, so that's ensemble number 1. Ensemble number 2 will be 2 times 10 to the minus 14. So those are minuscule amount of energy added to the system. And so the global mean temperature are all those gray lines that you can't see, right? And they're all stick together. And so here, under the forcing of climate change, lots of greenhouse gas changing, it's just warming, and the variability around the mean, which is that black line, is pretty small, right? And it makes sense, right? It's the global mean, just conservation of energy, not much can happen. The problem is when you start looking at things beyond the global mean. And this is, each panel is one of those ensemble members, and it's looking at the wintertime surface temperature linear trend over like a 20-plus year period. And you can look at your favorite area, and where is Belgium here? It's there. So you don't see it, but this is US-centric view. But I mean, what you can see is that from one ensemble member to another, there's a huge range of values that you're seeing for something that's pretty big. I mean, it's just surface temperature, wintertime average, linear trend. I mean, you'd think you might be able to capture that. And so this is what the model generates internally from just the physics that is present in the model. So if you want to have an idea of what it makes to, say, from this, say something actually happens in the world, and instead of going on this trajectory of warming, someone in the world becomes smart enough and decided we'll do something to reduce the warming, right? Hypothesis. And so you could say, okay, so how do I know that what decision I'm making here to change the trajectory of the world will actually be different from this? Because the real world will be one of those, well, probably slightly different, but one of those. So how do I know that all those policies that I've made will be beyond the noise that I'm expecting to see? And so this has become a very, very useful way of thinking about the world, but it has multiplied by a factor of 30 the cost of running the model. Because now there is never anyone who will say, just run the model once and you'll have the answer. We'll have to run the model multiple times, 10, 20, 30 times, depending on how much statistics you feel you need to have. So with that, CESM1 was released about 7 years ago. And it was discussed in this paper. And then, as always, we participate we do a lot of simulations that are being analyzed by people around the world. And they write papers and they rank models. And this is my favorite paper because CESM1 is sitting on top. And it's just some broad measure, right? So the model is not the best model in absolutely everything, just in most things. And it's better than GFDL, which is always nice. And but this has two messages, right? We're starting from a really good model. There's a lot of really good science that can be done with this model. So how do you move forward? And actually, so this is what we do, and we start looking at some of the things that we feel are the biggest impediment to do the science that we're interested in doing. And so even though the previous figure was showing temperature and precipitation measure, it was at the global scale, very, very broad measure. Here we're seeing, okay, so this is CESM1. And these are the observations, and this is the difference with the observations. And so it's on this scale, and the observations are on this scale. So the bottom line is that most of the Amazon is really dry compared to the observations. And so we can do this analysis, and we can say, okay, we feel in all those things that are not working so well in the model, and there's plenty of them, and I'll discuss some others later, how do we try to tackle this? And so this is kind of an intermediate version here called 1.5 that we had about a year ago. Those were simulations we were doing about a year ago, and Rich, who is in the back of the room, so he's the one responsible for this. But he's also responsible for the improvements. And so overall, we're still dry, but we're not as dry as we used to be. And so this is kind of the process. What are the biases of the model that we want to address? And then how do we go about it to try to eliminate that? And then another aspect is really, as I mentioned earlier, trying to build processes. What are the processes that are needed? And you probably won't be able to read this slide, which is too bad because it's really interesting. It comes from AR5. It's not the chapter I wrote. So, so this is the carbon cycle. And so one of the big questions is how the carbon cycle will respond in the future if in the case of the warming. And if you look. These are, for example, the net ocean flux is, say, on the order of 2. But it's a huge balance between 80 coming down, 78 going up. So there is a lot of really big fluxes that we have to capture to get something where the change is actually much smaller than the size of the original flux. So the change is really what we're after, but we have to capture all the fields that will lead to all those processes, and it's both within the ocean with very, very different timescales, whether you're looking at the surface or the bottom of the ocean. And if you start looking at things over centuries, then processes that are acting over those timescales are starting to affect the very deep reserves within the ocean and the land. And so this is one of the other drivers. And that means we have to build a model that captures all of that. And that starts becoming a little bit more difficult than our standard, let's get a bunch of physicists and numerical methods people, because we don't know anything about plants, right? Or most of us do. Or we're not familiar with hydrology. And so the field becomes much more heterogeneous, and you have to start bringing people with experience in a lot more fields than the standard. And that's the evolution from the climate to Earth system model. So how do we do? So this is for CESM1 again, results. So these are the observations at Mauna Loa, which is the long-term record of CO2 from 1958 up to 2005 or something like that for this paper. And so this is what CESM1 was showing over the 20th century. So incorporating all those processes, then you put anthropogenic emissions, and you let her rip, right? And this is the CO2 that it's showing. And you're like, well, it's not that bad, right? We're on the same scale. And but then you're like, okay, but at the same time, we're seeing that the bias is hugely increasing over time. And so here, the part where you would actually try to understand how well the model does in terms of projections, you're like, well, this bias is becoming worse and worse. And so similar to what I was showing about the Precip, then the land model went back and said, okay, so this is what the model is doing now for the change in the terrestrial carbon over time. So, and I'm sorry, I'm using things that's just different working groups have given me, so it's the reversed sign to maybe what we would be thinking. So basically the soil carbon is being lost to the atmosphere over time at a very significant rate, and that's why you get this feedback. So there is more and more with warmer and increasing CO2, you get more and more that's being released. But the observations are showing this. So here you know that this is not good. Right? So this is then within the people are like, okay, what is wrong? And in this case, a big chunk of this was the representation of the carbon cycle in it, but mostly its interaction with the nitrogen cycle and how those affect the way plants can uptake CO2. So with all that and all of those and many other aspects, we've built CESM2. So what is CESM2? If I were to show you a CESM1, all boxes would be pretty much different. So we've basically refactored all aspects of the model and included some new ones. For example, a representation of surface waves, because that drives some of the internal ocean mixing. And so this is the work that I'd say 200, 300, 400 people participated in. And then all that is brought together usually through the different working groups. And then slowly but surely we start putting, not sure but surely, but slowly we're putting all those pieces together. And then the fun begins, right? So you put all this, so people work on this for about 3-4 years. So as soon as we're done with the model, people are already thinking about, so okay, what's next? And then when there is this cycle of publications, that's when the biases are coming, and we know, okay, screwed up this, screwed up that. So this is a process that took 4 years or something like that, and then we put together, and then we start looking at it as a coupled model. So because what we're after is really the Earth system model. It's not just the atmosphere in isolation or the land in isolation. We want to make sure how the whole thing works together. We can cut those feedbacks if we want to, because it really helps our understanding of what's going on. But the ultimate goal is to make it work as an Earth system model. And then surprises happen. And this one is, so it's a really messy plot, and you don't need to actually look at this. But one of the features that we're seeing here is over time, in some of those configurations that we thought the ocean looks great, the atmosphere looks great, sea ice looks great, let's just put it together, and then it looks bad. Because at some point in those, the Labrador sea ice, so northeastern Canada, just shuts down. It just gets completely ice covered. So this is where you should be starting and staying. And some of our early versions where the ocean was using an old atmosphere were perfectly stable. Man, you run 120 years, 150 years, perfectly stable, very easy. But then you put the atmosphere, and the atmosphere where, like, we know fluxes at the surface are not correct. Clouds are not correct. So let's fix those. Valuable goal. Then we put that, and it goes to hell. Right? And it's the usual thing of not being able to fix all the parts at the same time. So this is what we were facing last June. And I almost had the mission accomplished banner out in June, and then a few weeks before we started those. And they were like, oh yeah, we can deal with that, it's pretty easy. Just tweak with some parameters. And then that took about 6 months or 5 months to figure it out. And so finally, and so one of those, and the scale is different because it's slightly different measure. But this is what we were facing. And it was very intermittent, right? It was it was not like you could just run the model for 20 years and then it happens. So this, we were gonna stop at 100 years and call it good, this one. And then the ocean group said, no, maybe the climate variability. It'd be great to run 120 years so that we can look at ENSO better. And shouldn't have never listened to those people. This is what happened, right? So now we're like, okay, we have to fix this. And as I will mention later, this is a blessing that we can actually do those 120-year simulation in a reasonable amount of time. So this is what we're facing, and then finally a solution was found, which, to be brutally honest, we know we're getting it right for the wrong reasons. But with the development path that we have at this point, we decided that the atmosphere was absolutely necessary to have improved the way we wanted it to be. And so here, by accident, there was improvement coming from the ocean side. It is probably not completely accurate, but it's representing something that we know we should have, and we might have that with a very, very high resolution model that we don't have. And so here it's tapping into an ocean heat source that is probably not completely correct, but it's saving us. So we'll take that. But also, I mean, we'll be completely frank, right? I mean, we'll be presenting the results and showing this is probably not right for the right reasons. And then we build a model, we solve that, and other things at the same time. And then one of the tests that you do to the model is to put it in a hot climate. Then you multiply instantaneously the CO2 that's present by a factor of 2 or 4. And you just let the system equilibrate, and that gives you a measure of what we call the climate sensitivity, which is just a broad response, a broad measure of the response of at least the global temperature to a CO2 change. And those kinds of experiments have been done for the last 40 years. So there is a lot of information there that we can compare to other models and observations, trying to see if what we're seeing is anywhere close to reasonable. We don't tune it in our model, but we have to see if it's physical. And so this is where a version of the model where it did go to unphysical. So this is a plot where you start at year 0 is when you change the CO2 by a factor of 4. So it's going to warm up really quickly, right? At the top of the atmosphere, lots of warming there, and the rate of increase will be really fast. And then the top of the atmosphere, which is how it equilibrates internally, you just get rid of the heat, either you radiate it or you take it in the ocean. So the top of the atmosphere is going to converge to 0 eventually. It takes time. But this is what the second best model in the world is doing. And so this is what you should be expecting, is that it's going to be warming, and it's going to trend to 0 with time. Each dot is a year. And this is what this version of the model was showing. And it's basically showing that there was no sign whatsoever of stopping, right? So if you start computing what we call the climate sensitivity, at this point we were like, well, this is going to look like infinity, which we know is unphysical. And then there were a couple, and then there was this glitch too, and which was when the chlorophyll in the ocean model became NANs, and which are not a real species in the world. And so it made the ocean completely transparent, because that was the way, if you have NANs, then the lookup table, it's one of those things, and then the ocean is transparent, so the heat that comes is just deposited way down below in the ocean instead of being at the surface. So you warm some, but then the heat is being taken by the ocean. You just change completely the way the system works, which is kind of cool in a way, right? It's an experiment. So I don't know if we'll discuss this one in a paper, but I think we will, because there was another part to it. It wasn't just the chlorophyll. The clouds were just going berserk, and then we're like, okay, this is where we know we've got to do something, and then that took much less time. We must be getting better at fixing problems, and so it took about a month to figure out, and then those systems, I mean, it's 1.5 million lines of code, and then you have all sorts of changes, and of course, you do the simulations, and then you forget to put the fix on the chlorophyll, so you get the chlorophyll bug again. But then now we have it fixed, I think. So then okay, so you go through those big things. And so along the line, you can start evaluating where is the model going. And this is what we call climate scale score, which is some broad measure of basically dynamics in the northern hemisphere. And you can compare it to reanalysis, which of course are perfect. And then you start from CESM1, and this is a slide that's slightly older than where we are now. But what happens is that for a while, the introduction of all that new physics and new model representation actually does make the model worse. And so this is a very slow process. It does make a model worse, but then you can work on putting all those pieces to work together. And then you end up with a model that ends up being much better from the original one. Other measure, precipitation. And here, and we'll just be comparing to CESM1, the large ensemble that I was mentioning earlier. These are the global mean, Precip, and the root mean square. So just very broad measures. So we have a significant decrease in the mean, significant decrease in the root mean error. So how different are we in both pluses and minuses? I mean, you could have 0 as the mean, and then very large values, and so there would be a very large root mean square. But you don't want that. But one thing that has been plaguing a lot of climate models for a long time is this feature that we call the double ITCZ. So the real world shows something like this. Precip, there is a band, at least in the northern winter, a band of precipitation going into the southern hemisphere, and then a pretty much straight across band of precip. And this is what CESM1 does, just pretty much straight across, and we call it the double ITCZ. And then with this model, this is a really key feature here, is that we finally, for the first time ever, we've been able to really reduce the latitudinal extent of this, longitudinal extent of this feature. And so they represent much better this. And this is kind of critical, right? So this is ENSO. This is the feature that will have a lot of responsibility for the internal variability of temperatures, but also it will affect remotely all the climate. Snow, no snow over Colorado, La Nina, El Nino, that sort of thing. So if you want to be able to capture those regional features, you want to make sure that you get the overall structure right. And so same thing for this power spectrum. And then one thing that I guess we don't totally know why, but I'm sure we'll find out. But one thing that has happened is looking at some of the modes of variability. Again, you want to capture the way the system works, right? So modes of variability is one of the ways of the interaction between ocean and atmosphere that you want to capture. And so these are the observations, and you're looking in colors here at the precipitation field and the wind. But it doesn't really matter what the details are. But those are propagation is the Madden-Julian oscillation from our own Ronald Madden. And so this is a feature that's very pronounced and has, and Mitch knows a lot more about this than I do. But it's a very key element to the variability of the tropics. And this is what CESM1 does, and you don't have to have a PhD to realize that those are not the same. But then, something happens. I was going to put that cartoon, like beginning and then a miracle happens. And this is basically, it's not quite, but we don't fully understand why it went from this to this. But we're very happy with this. And this is, again, a sign that the model is capturing the way the real system works. So the science freeze of the model was done on February 24th. And we had bubbly at 9:45 a.m. It's a very nice way to start the day, I can tell you. And then, so what's going to happen next? So we're planning to release in June of this year, and it takes about 3 months now. That's code cleanup and documentation, and then final testing. Make sure that everything that we feel should be right is right. And then papers will be submitted right around that time to a special issue. And then I want to spend the last 10 minutes on how we're going to use this model. So as I mentioned in that ranking of the models, that was CMIP 5. So it's the climate model into comparison project phase 5. And then, so we're starting now the phase 6. And they're looking at a variety of aspects, and then they ask people, so what do you think are the interesting questions we should be addressing? And you should never do that to scientists because they come up with a huge list of MIPs, so model into comparison projects. And now there's one about aerosol and carbon and all sorts of things. And so the models now will be exercised in all those different fashion, which I think is wonderful because then dozens, hundreds of people are going to be looking at the model as it's being pushed in specific aspects, looking at specific questions. And so there is, so we're looking, and one thing that we were able to get is 250 million core hours for Yellowstone usage before it's being turned off at the end of the year. And so this is all that we have for what is being called the deck, which is the very standard simulations that everyone will absolutely be doing. And it's like the 4 times CO2 that I was mentioning, and then the long pre-industrial control, where you can understand how the system works when it's not being forced by anything. So, yeah, I'll skip that. So what does that mean? It means that we're going to be running about 20,000 years of the model to do all those experiments. And that's with the standard 1 degree version. We have basically the low top, which we call CAM, and the high top, WACM. And we're going to be using a lot of information from this one to feed into this one. So that's why we have to have both a lot of years for each of them. And we're going to be doing a small amount of the high res just because in a way Yellowstone is not the right machine to be doing those high res. And unless we kick everyone out, which I'm fine with, but otherwise we don't have the computing time available. And we're going to be generating petabytes. And I really would like to thank the work that I've been doing with CISL on data management, workflow, and all that, on how to handle all those petabytes. So we have approximately 9 months, although that's shrinking quickly. But it takes about 4 months between now and when we can start doing all those historical 1850 to present and future. And it's because we have to go through a certain number of iterations to get all the parts of the model initialized properly. And some of those are everything that's related to the biogeochemistry. The whole ocean biogeochemistry, even deep down, which would require thousands of years of simulations, or have to be initialized, because otherwise you're going to be stuck with drifts in the model. Then it's really hard to get the response from the drift that's present in the model. And so there's going to be a step of about 4 months here, and we're doing this one right now. It's going to be finished on Monday, so we can start this one next week, or because of spring break, we might have to wait a little bit. So we have a sequence of things well laid out that will keep us busy until June or so, and then that's when we're going to start hammering Yellowstone really heavily, and because then we can start doing ensembles and things like that. So June is when we want to have the model ready to go and get ready to do a lot. And as I mentioned earlier, it's been tremendous that we've been able to, with a lot of help from CISL, a lot of people in this room, to get a model that even with that complexity that we've put, is capable of getting 20 years per day. So 20 simulated years per day. So those 100 years take about a week if we have access to the machine. We don't always have access to the machine, but say it takes a week or 10 days. This is actually a turnaround that is amazing compared to a lot of climate models. Very few people have that. And then this extremely complicated and extremely complex version of the whole atmosphere has a full chemistry. And people can blame the chief scientist for that, because we've put 220 chemical species in there, which is totally crazy, right? But it's going to be an amazing tool to use, and so I said it was fine to pay the price, but we still get 6 years per day for something that's extremely complex. And so what we're going to do is run on Yellowstone until the end of 17, and then it's probably going to be turned off. So we're going to be using this to do a lot of our CMIP6 simulations. There will be, for the key ones, there will be other simulations performed on Cheyenne, definitely the quarter degree, and some of the lesser priorities on the 1 degree. But I think one of the key thing here is how quickly we can get the data out, and whether it's post-processing, the fields are usually put on a bunch of fields, history output, a bunch of fields at a single time or a collection of time. So you have to transform that into time series because that's what CMIP wants. So there's post-processing, putting the data to the Earth system grid, and then hopefully you do the analysis quickly. Last year, for CMIP5, by the time the simulations were done, this took 6 months to do the processing. Here we're talking about doing it in a few weeks within a traveling window. So it will be continuous instead of just, we're done. Now let's turn the switch on for this part and spend 6 months. That was a very stressful time. So here with the workflow that's been done, and a lot of work on post-processing by CISL, this is going to be much, much faster, which means we can put the data out for people to do the analysis. And we can write papers, and this will be a key place for the analysis platform here. And with so as a kind of like a next step of CESM, this is one example. I think one of the cool aspects is looking at regional refinement. Models are super expensive if you have to use a constant grid for the hemisphere of like 25 kilometers, which you want if you want to be explicitly representing close enough the tropical cyclones, right? And flows around topography and all those things. You want to have enough resolution, but it's really hard to run that, and so globally. And so having a stretch regional refinement is a great tool. And thanks to the ASD, we've been able to do that. And so this is kind of like the next generation. Maybe some of it will be used for CMIP6. So some of the lessons learned, all this is that we really had to think about this as always coupled all the pieces together. And it was really clear that working in just atmosphere ocean was not sufficient. And I would say that we would not have been able to do the 150 different configurations that we did to build a model. It took 150 configurations, well, 145. And we would not have been able to do that without the sufficient throughput that we were able to get on Yellowstone, and I would argue a very stable environment. So it's been critical that Yellowstone is available most of the time. And then and it's a really difficult problem. And so it does take a lot more time and a lot more expertise every iteration of this process. So conclusions, well, it took about 5 years and many people. And I would emphasize again and again that this is about developers and analysts of people bringing theoretical ideas, observations, and not just code. That's what makes a good model. And I would argue that it is significant to very significant improvement over CESM1, which is not a small feat. And then CMIP6 will really help understanding how well this model performs under a variety of conditions. And I think it will be both great and disheartening to see some of the things that we'll be failing. But again, that's part of the process of going to the next version. So with that, questions, comments?